chemistries, new molecules that will enable us to capture these metals. It could be gold, it could be things like cerium or neodymium or whatever, so that we can effectively recycle them.
Hi, I'm Dr. Jed Macosko at academicinfluence.com and Wake Forest University. And today we have a special guest visiting us from Northwestern University outside of Chicago. And this is Professor Schatz. So we're glad to have you on this show, Professor Schatz. It's good to see you.
Thank you very much. Yes, I'm pleased to have a chance to talk to you.
Great. Well, we'd love to know a little bit more about your current research. You have a lot of grad students, postdocs, maybe some undergrads working for you. And what is it all going towards? What projects are you most excited about?
Yeah, so my research over the last, I've been a faculty member for 45 years, but I would say, especially in the last 20 years or so, that's still a long time, we got very interested in nanoscience. Okay, so that's been the highlight of that of what I've been involved with. Of course, I do theoretical chemistry and computational work and things like that. But it's easy to look at the program of research that I'm involved with and say that what I'm doing is using the basic tools that I have available for me in terms of computational chemistry and theory. And we're applying them to problems that relate to the nanoscience field in the broadest way, okay, and in sort of many different directions. And so, we got involved initially in understanding just what are nanoparticles all about, okay, particularly the silver and gold nanoparticles and other metal particles that have unique size-dependent optical properties. So optical properties kind of got pushed on us early on as being an interesting area in the field, and we've worked very hard in a lot of different directions of that topic over the years. But we also do things related to structures of not only the nanoparticles, but also the molecules that you put onto the nanoparticles. The interaction of molecules and nanoparticles is a very interesting topic. It can go in many directions. It can include biological molecules like DNA interacting with nanoparticles or peptides. So we covered a lot of different topics. I always say it's like, how many projects do I have going on right now? Like 20. Okay. But to me, they're all exciting projects where we're trying to learn, in many cases, about properties of molecules, nanoparticles, optical properties, and sometimes other properties, particularly structure and thermodynamics, that are often cases where it's just, we can use computational tools to study and understand these things and provide important insights that are crucial for understanding experiments and for making applications in a wide set of directions.
Very cool. Well, yesterday we spoke with Nobel Prize winner Bob Curl, who lamented the fact that the C60, the fullerenes, never really found an application. Junior never grew up and got a job, is how he described it. But yours, it already sounds like you're hinting at applications. Can you share some of the exciting applications of some of the research that you and your students have done?
Oh, sure. Yeah. Actually, the fullerenes have. Once in a while we've played around with the fullerenes, and I know Bob Curl, and he's a terrific guy, absolutely. And and the fullerenes did find a somewhat unique application in terms of a field that we have worked in the area of organic photovoltaics, okay, and so on. Although it turns out the funny thing about it is that it was like, for a while there was a fullerene that ended up being like the best possible molecule to use for organic photovoltaics. But then, of course, everybody said, oh, well, yeah, but you don't really want to do that long term. And so a research area that we've worked on in the last few years has been finding molecules that can replace the fullerenes in organic photovoltaics. And so that's been an interesting topic. And the photovoltaics topics is I think, a good area that where I mean, I don't think of us as having been, necessarily, the leading edge players of that field, but we certainly have been involved in it, and it's been exciting to watch it. And so that is in a field that has, evolved quite a lot over the years. Yeah, where we kind of got more involved is it had to do again with these metal nanoparticles, the silver and gold particles, and understanding how you can use them for various applications. Of course, that's kind of an older topic in some respects. I mean, people are already making topics. I mean, Michael Faraday studied the properties of gold nanoparticles for about a year in the 1850s, so it's an older topic, but at the same time, in some respects, it has a very sort of modern version of what's going on that began with the discovery of all the tools for nanoscience that we all use, the scanning tunneling microscopes and things like that. In addition, there were a bunch of exciting spectroscopic tools that came along that went beyond what Michael Faraday was doing, that were discovered starting in the 1970s. And so that for me was a big deal because of the fact that there was a technique called surface Raman spectroscopy that was discovered here at Northwestern by one of my colleagues in the 1970s. And so that proved to provide lots of interesting challenges for doing theory and computation. Then there's directions and applications of the gold particles and silver particles and so on that have gone in many different directions, particularly having to do with how to attach molecules to these particles and then use the particles for sensing applications. And then there's been exciting work done here that has had to do with attaching DNA to gold particles and then using that combination of things both for sensing applications and more recently for medical therapeutics, which was a surprise that could actually be done. And so this is the work of another colleague, a guy named Jed Macosko, a very exciting person. Then there's other biological applications. One of my other colleagues, a guy named Sam Stoop, has done some very exciting work in which he's figured out how to make peptide-based materials that form nanofibers. And so it turns out those have both therapeutic and applications in making structures of various types where fibers have useful mechanical and also biological applications.
Very cool.
So it's just goes on and on in terms of where you can find exciting science to get involved with. Right.
That is really exciting stuff. So it's nice how you talk about a lot of your fellow chemists and colleagues at Northwestern. Definitely, it's nice just to see that you're promoting other people's stuff too. But when you walk into a seminar room to give a little talk about what you and your group have done, what applications do you mainly like to focus on those first few slides? Things that have made it into the everyday public, sensing or therapeutics or whatnot.
Yeah. So the sensing and therapeutics has been one that we've talked about. That for us, that's more in the past. There were fundamental discoveries that were done about 10 years ago that sort of established what was possible in that direction. So I haven't been pushing that so much. But another thing that actually was discovered 10 years ago, but which had a more recent life of its own, had to do with understanding, again, so these gold particles. It turns out you can make arrays of gold particles, okay, and they have some exciting properties, optical properties, and where you can combine together the excitation of gold particles with light in combination with the properties of the arrays, where you have diffraction that's possible, things like that. And so that combination of two things, the excitation of the individual particles and the diffraction, ends up leading to optical properties that went in directions that I never could have predicted. But it was one of these things where we discovered all this stuff initially on the computer, and then it was like Oh, and at the time, there were really no experiments which showed the effects that we thought were interesting. But eventually, people got doing those experiments. Initially, I was told that isn't going to work. Okay, but later on, they did the experiments, showed the interesting optical effects, and now it turns out that sort of morphed into a way to make lasers. Okay, and so we all had to become, sort of experts in the laser area that has to do with these optical properties, and then coupling those into either laser dyes or into things like semiconductor nanoparticles that can laze. And so that combination of things ended up being an area that has been a very active field in the last 7 or 8 years.
Wow.
And so, yeah.
Did that particular project point to something that would be something consumers could use with some sort of interesting optical properties? I know it's not going to give us like a cloak of invisibility like Harry Potter,
No.
but maybe it would give us some kind of
Yeah.
display or
So unusual optical properties, right? I mean, again, at this point, it still hasn't translated itself into into practical lasers that somebody's going to use in the grocery store. Okay, but it could. Okay, I mean, it's always a matter of just, the laser business is one where, the applications are all about who's got the best, the best and the cheapest and all that kind of stuff. And so yeah, there's always issues about, is that can it go in that direction? Maybe there's applications in the communications business. That's an area that we're exciting right now, having to do with just understand. There's an area called quantum science that has kind of emerged in the last few years that has to do with things like secure communications. So it could be that that's going to end up being where the applications will come. There's optical devices, photonic devices that have already appeared to a certain extent, but which could evolve. Okay, get rid of the electron circuits in your devices and have them all involve just beams of light that are being transmitted within your device, things like that. So.
Wow, that would be incredible. Well, it's really exciting to hear the kinds of things that you're already doing in your lab. Are there any things that you still want to accomplish? You have a lot of career left ahead of you. So are there things sort of on the horizon that you want to talk about?
Well, we got involved in some areas that were non-traditional, at least for me and my group. Okay, but which I think are exciting. We're involved in a center right now that's trying to solve the problem of the fact that right now we have all these wonderful cell phones that we love, and so on. They're full of materials that are things like lanthanides, which are sometimes called rare earths. They're not that rare, but nevertheless, it turns out it's an environmental catastrophe to both extract them in mining and also throwing them away into garbage dumps is a terrible thing. And so you'd like to recycle all these guys, but the recycling, the chemistry isn't known basically for the most part for recycling of lanthanides, or it just doesn't work very efficiently right now. So I'm involved in a group of people, one of whom is my colleague Fraser Stoddard, is a famous guy, where we're really trying to figure out how to design new chemistries, new molecules that will enable us to capture these metals. It could be gold, it could be things like cerium or neodymium or whatever, so that we can effectively recycle them and get them out of the garbage dump business.
Oh, wow. Well, that would be great. We just spoke with the guy yesterday who started the green chemistry project at the EPA back in the 1980s. And he would be very proud of you for figuring all this out. And yet another example of how we as humans can take better care of the things that we've been entrusted with. So that's awesome. Well, thank you so much for sharing all these great things with us today. It's just been such a delight to speak with you, Professor Schatz, and we really appreciate you taking the time.
Happy to do it. Thank you very much.